It's an honor for me to introduce Dr. Charles H. Bennett. Dr. Charles H. Bennett graduated from Croton Harmon High School in 1960 and from Brandeis University, majoring in chemistry in 1964. He received his PhD from Harvard in 1970 for molecular dynamic studies, that is, computer simulation of molecular motion. For the next 2 years, he continued this research at Argonne Laboratory. Since coming to IBM Research in 1972, he has worked on various aspects of the relation between physics and information.
Thank you. I'm going to try to tell this lesson that I gave the brief preview of. I guess there were some, thought the audience might be different, but the audience seems to be almost entirely the same as it was before. So you may see some things repeated. I said, of course, well, my outline is I'm going to speak of what ordinary information is, classical information, which really everyone knows, even non-scientists, how quantum information is different. Entanglement, I'm going to try to explain that and what it's good for. Something about quantum computation and error correction. And this is of a more philosophical direction. That is what quantum information can tell us about the impermanence of information in our world. Then I have a few extra topics at the end if people are interested in trying to explain in a simple way, using things like the two-slit experiment, how the quantum speed-ups work, like the speed-up in the Shor's algorithm. We probably may not get time to get to that. But I guess this slide has been taken over and used by other people, which is very flattering. That is that what we think of as information is part of a larger subject, and most people who are non-scientists, and even most people who work in other parts of science and in information technology, are rather unaware of this larger field. I've sometimes said that it is related to classical information in somewhat the same way that the complex numbers are related to the real numbers. The real numbers are an interesting and useful subset of the complex numbers. And most people who know about numbers don't know about complex numbers. And yet, if you understand complex numbers, then certain things about the real numbers appear much more simple and intelligible. You might say it's a simpler, grander theory, which we should take into our minds, not so much because it might be useful, but because it achieves a better understanding. Well, as I said, information is the mathematical abstraction of distinguishability of physical things, and everyone knows that information, you only need to distinguish two states, and then if you have a number of bits, you can encode a decimal digit or a letter of the alphabet, or even to arbitrarily approximation a color of the rainbow. And everything you want to do to these bits or to the information they represent can be reduced to very simple operations. And that the physical form of these bits can be abstracted away, thereby making possible ever cheaper and ever faster bits, and the many benefits that we have from Moore's law. Now, this abstraction is taking something that was originally a physical idea. When we speak of calculation, that comes from the Latin word for a pebble, and as taking it into a purely mathematical idea. But there are some physical properties of information which are still present. Everyone knows that you cannot send information faster than the speed of light, and if you don't like some information, you can erase it when you no longer want it, and you can copy information without disturbing it. Well, those things are not quite so simple. Well, certainly it is true that it cannot travel faster than the speed of light. And even the phenomenon of entanglement, which I'll speak about in greater detail, only appears to violate it, but does not violate this. The idea that you can erase information when you no longer want it is true, and yet some of the early work that I did with my mentor, Rolf Landauer, was concerned with discovering the fact that the heat production by computers is intimately connected with the erasing of information. So erasing information is not a purely mathematical process. It's a process that is related to physics as well. And then this notion that information can be copied without any penalty, except perhaps some kind of copyright violation, is actually not true of quantum information. It's true of classical information, and I'll try to explain the difference. And as I said, that chemists and physicists, when they think about distinguishable states, have long known that the information in atoms and photons and so on, in general, cannot be read or copied without disturbing it. And there's this phenomenon of entanglement whereby if two particles have interacted, or two systems have interacted, and then moved too far apart to influence each other, they can exhibit correlations in their behavior that are too strong to be explained by imagining that each one is in a state that it got into by the result of the interaction, and yet too weak to be used to communicate from one to the other. So this is these are some serious differences, especially this impossibility of reading or copying it without disturbing it. But there are also some big similarities to classical information, and that is that the state of any quantum system can be encoded into these two-state systems, which are now called qubits, and that any processing of that can be done by operating on them one and two at a time. And in principle, these can be encoded or translated from one quantum system to another in just the same way that classical information can be encoded in pebbles or holes in a card or electric charges. So this gives the hope of building a quantum computer in which the science of the hardware of the computer will be separated from the science of the software in much the same way as we have for classical computers. It'll just be much harder. Well, this was this metaphor here, which I suggest to any of you who would like to try to explain quantum information to an audience at a dinner party, and if you start speaking of Hilbert space, or if you want to explain an entangled state, the simplest space in which you can do it is a four-dimensional Hilbert space, which is the tensor product of two-dimensional Hilbert spaces. And every time I do this at dinner party, my wife gives me a look, and the person that I'm trying to explain it to asks to have some more wine or something like that, or they do something to divert the conversation. So so as I said, that the quantum mechanics obeys well-known laws, and these, of course, were developed by people who were chemists and physicists, and they didn't realize that they were discovering laws of information processing. But that's over about the last 20 years. That's what this quantum information science has been doing. It's been reinterpreting the laws of quantum mechanics that were discovered in the early 20th century as laws of information processing, and thereby producing a simpler and grander theory of information processing. Well, what are these laws? It says that to every physical system there is a space with a number of dimensions equal to the system's maximum number of reliably distinguishable states. And every direction in that space corresponds to a possible state of the system, and the spontaneous evolution of the system, if it's not being observed, is what amounts to a rigid rotation in this space. Can people hear me? Yes, okay. So here's all the mathematical details of it. There's a few more laws. And if you put together a compound system, then this is getting too complicated. Besides, there are religious controversies about this last axiom. Some people think it's not necessary. So let's try to boil it down to something, the simplest element. It says the really distinguishing feature of quantum information is that between any two reliably distinguishable states, there are other states that are not reliably distinguishable from either original state. And this is illustrated by, in a convenient way, by the polarization states of single photons. And this is how they behave. So imagine these photons are propagating in this direction here. We can imagine them to be, this is a perspective view, horizontally polarized or vertically polarized. And photons of those two kinds can be reliably distinguished by passing them through a properly oriented crystal of a birefringent material such as calcium carbonate. And then the horizontal photons will go straight through, and the vertical photons will be deviated and come out in a different path. And if we put counters here, we can use each photon to carry a bit. But if we put in photons that are, the photon can be polarized at any direction, perpendicular direction of its propagation. We put in photons polarized at some other angle. When they get to this crystal, instead of being deviated by some intermediate amount, as you might expect, they behave randomly. And some of them go into this beam and become horizontally polarized, and some of them go into this beam and become vertically polarized. And so this imperfect distinguishability is the physical manifestation of the idea that the mathematical representation of this photon is a direction in space, and when the directions are not perpendicular, are not orthogonal, the states are not perfectly distinguishable. So the horizontal and the diagonal photon are in principle imperfectly distinguishable, not because of some limitation of the observing apparatus, but because they are not perpendicular, their mathematical directions are not perpendicular. So this is the mathematics that underlies this imperfect distinguishability, and that's really all you need to build the quantum information theory. Well, in fact, it leads also to one of the early applications of quantum information. That is that there are states that are distinct but not reliably distinguishable, and that's what's used for quantum cryptography. But before I describe quantum cryptography, I'll say something about cryptography. And probably the fundamental theorem of cryptography is called the one-time pad, or Vernam cipher. Probably, how many people are familiar with the one-time pad here? Oh, well, this is it's worth explaining then. So this is a way of sending a message in perfect secrecy over a public channel. But you have to plan ahead. So the person who wants to send a message, before they send a message, they have to share a random bit string called a cryptographic key, and they make this bit sequence by tossing some coins, and they make a copy of it and just take it to the receiving location. So the sender has a copy of this key, and the receiver has a copy. No one else in the world has a copy of it. With that preparation, they are now able to send a secret message over a public channel. And the way they do it is when the message comes along, they take the message and XOR it with the key. That is, they add without carries base 2. Or to put it another way, wherever there's a 1 in the key, the message bit gets flipped. And wherever there's a 0, it is left alone. So you see that if you take the message and you flip half the bits at random, you have really completely scrambled it. And it can be, therefore, sent publicly without leaking any information to an eavesdropper. And then at the receiving station, the key is then used to flip the bits back that have been flipped at the sending station and therefore recover the message. So this is a perfectly secure crypto system, but it has the handicap that you can't use the same key again. Can anyone say why? What would be the weakness or the security risk of using the same key and sending 2 separate messages? So with this key is a kind of a non-renewable resource, and this system is used in I think fairly widely in official communications amongst embassies. I know it was used in the Moscow-Washington hotline. And I believe another example of it was the use in communication with Fidel Castro to Che Guevara when he was in Bolivia. Of course, real spies don't do their adding base 2, they do it base 10. So you can see here's the message, the key, and the cryptogram, and these will all add up base 10. Well, the quantum cryptography uses imperfect distinguishability to avoid the need to hand deliver the key. And so it begins with the two good guys, Alice and Bob. These are the traditional names they use in cryptography. This was introduced just so that you can speak of them as him and her. And then this Eve, the eavesdropper, is just sort of a bad English pun. So she's the enemy, and she has the power to listen to all of the classical messages between Alice and Bob, but not to change them. And of course, she can try to intercept these photons also, but if she does, she may alter them. Because as you saw, when you attempt to measure a photon without knowing what its polarization state is, you are likely to change it. And the outcome of this kind of protocol is that Alice and Bob will first, Alice will send a quantum transmission to Bob that includes these 4 different non-orthogonal states. Then they'll have a discussion about it, and they will assess the extent of eavesdropping, and if there has not been too much eavesdropping, they will distill a secret bit string, which they have high confidence is not known by anyone else. So this is actually better than carrying it in a box like this, because you know if you try to carry a box like that through an airport, they're probably going to want to open it up and look inside. So, or even if they didn't open it up, you might walk through a high-resolution CAT scanner, and so it could be examined without your knowing even that it had been copied. Whereas in this case, the only thing that's gone between these 2 people is something that if it were copied by someone en route, that the observation of this would lead to a disturbance which would cause them to reject this key, decide that they're getting too much interference, and therefore they cannot distill a key today. They should try again tomorrow. Well, that's the application of imperfect distinguishability to cryptography. But what about this notion of quantum data processing, of doing computations with quantum data? That is less well developed, but is the more exciting part of the field. As I said, any quantum data processing can be expressed in the quantum data can be encoded into qubits, and the processing of it can be expressed in terms of operations that act on one and two of those at a time. So let's look at an example of that kind of quantum gate. This is a diagram that's very similar to the diagrams that are used in computer science for manipulation of classical bits. So in a classical computer, each one of these wires would carry a bit, and then when they interact, the one bit would influence how another bit changed. It could do an AND or a NOT or an exclusive OR. In fact, the one-time pad that I just described uses the exclusive OR operation. That is the conditional flipping. Well, let's see what a conditional flipping looks like in the quantum case. Well, of course, we want to use two distinguishable states to represent 1 and 0. And we might call a vertical photon a 1 and a horizontal photon a 0. Now, I've got a green one here and a yellow one here, or an orange one there, just to keep them separate. So we could say, let's make an interaction between two photons such that the upper one conditionally flips the lower one. If the upper one is in the vertical state, meaning it's a 1, the lower one will get rotated to the perpendicular state from whatever it was. So that's the exclusive OR, or people in quantum information call it controlled NOT. And if the upper one is in the horizontal state, nothing happens to the lower one. Well, this is an example of a two-particle interaction. But because it's a quantum interaction, it has to obey the superposition principle. And if you give it a superposition of inputs, what must come out is the superposition of the outputs. So let's give this control bit, this control qubit, put it in the superposition of vertical and horizontal. In other words, let it be a diagonal state. And then what happens is the output comes out in the superposition of the second one being not flipped and being flipped. And in other words, we just take these two cases. If we give it the superposition of inputs, we have to come out with the superposition of outputs. Now, this superposition of outputs means that the control qubit here, which doesn't look like it's getting changed in a classical way of looking at this, ends up getting changed. So here it comes in diagonally, and what it comes out with is a superposition. This is why you need to think in four-dimensional space. A superposition of both photons being horizontal and both photons being vertical. Now that's an entangled or Einstein-Podolsky-Rosen state. I'll say a little bit more about it. Let's see. Yeah, I'll say a little bit more about it later. It's a state of those two particles which cannot be, it's not the same as both of them being diagonal or as both of them being any other particular state. It's a state that lives in this four-dimensional space. Well, why is the space of two photons four-dimensional? Each photon has two distinguishable states. And therefore, if I have the two photons, I can have them both like that. I can have them both like that. I can have this one, and I can have that one. So that's four states. I know that I have to have at least four. And by the superposition principle, any direction in that space, in that four-dimensional space, is a possible state of 2 photons. So therefore, this, the direction that's halfway between this and this, which is what I've got there, that's a possible state of 2 photons. And that is not the same as this. Let's go on a little bit, and I'll come back to that, because that's a slightly mind-boggling idea. But to say that quantum computing includes classical computing is to say that we ought to be able to embed the whole theory of classical data and data processing in the quantum theory. And this is not hard to do. We can say that a classical wire, something that carries a 0 or a 1, is just a quantum wire that interacts with its environment in such a way that 0 or 1 goes through, but superpositions get spoiled. And the interaction that's needed is just this one that I showed. And what will happen is if I put a 0 or a 1 through here, the environment will get a copy of it. But if I put a diagonal state through here, the environment will become entangled with it. And if I am not able to look at the environment, or the environment escapes from me, this thing will look as if it's been randomized. So you can say that a classical channel or a classical wire is just a quantum channel with an eavesdropper. And a classical computer is a quantum computer that is handicapped by having eavesdroppers listening to all its wires. So you can see that that is a serious handicap in terms of privacy, but it also turns out to be bad for the computation. If you take a quantum computer and you put eavesdroppers on all the wires, there's some kinds of computations it can't do as quickly. Now, I said before that the evolution of an isolated quantum system is deterministic. Of course, there are systems that interact with their environment or undergo measurements, and then this is not a distinguishability preserving process. But we can always view it as embedded in a larger system that is undergoing a distinguishability preserving process. So you might say that all you need to understand loss of distinguishability is to say a large system is undergoing some distinguishability preserving evolution, but you are losing sight of part of the larger system. And because you can't see all of it, the part that you have left to look at looks as if it's behaving randomly. Now, this notion was named by my colleague John Smolin the Church of the Larger Hilbert Space. Now, of course, this is somewhat of a pun, because in the United States there are churches, there are thousands of different churches, and they all have names explaining how they are different from other churches. And really, if you're not a member of the church, it's hard to understand these differences. And in a certain sense, when you use this kind of religious metaphor, it's really saying we look at the same world, but we see it differently. In the Church of the Larger Hilbert Space, it says that all evolution is distinguishability preserving. And if we think something that is random is happening, it's merely because there is a larger system that is evolving in a non-random direction, but we've lost sight of part of the system. So this doctrine only makes sense in the quantum context, where you can have an entangled state in which the whole system is in a definite state, even though the parts of it examined individually appear to be random. And this is sort of quite different from the view of impurity that is present in the Bible, where if you have any impure part of your body, therefore your whole body is impure, and therefore if your hand does something bad, you should cut it off. Well, anyway, so let's try to understand this entanglement a little bit more. So I said this state, which is intermediate between both photons being horizontal and both being vertical, is it actually is the same as between both, is this intermediate state between both being left diagonal and both being right diagonal, but it's not the same as both of them being diagonal. And the reason is that it would behave differently. Well, you can work it out mathematically. This is just a direction in a four-dimensional space. But in terms of their behavior, this state, if you attempt to observe the first the green photon along any axis, it will be equally likely polarized one way or the other way. Whereas this one, there is a particular axis along which you could observe the green photon in which it would behave reliably. So this entangled state is a state which is a definite state of the two photons together, but if you observe either one alone, it looks random. This was pointed out by my colleague Michal Horodetsky. He said this fact about entanglement was discovered by Schrödinger. He said it's as if you could say, if my desktop is a complete mess, it's covered with all kinds of papers that are in complete disorder, and some old coffee cups, and also the drawer in which I keep my clothing is a complete mess. There's an odd number of socks, and nothing is folded up, and there's other things in there that shouldn't be in there. And so suppose I'm a child, and my parent comes around and says, "Oh, you have such a mess in your room. Look at how messy your desk is, and look at how messy your clothing cupboard is." But the child, if the child knows quantum mechanics, could say, "Oh, my room is in perfect order. My desk is entangled with my clothes. If you look at the whole thing, it's not in a mess at all." So you could say that the two photons are in a definite state of sameness of polarization, even though neither one has a polarization of its own. Now, in the laboratory, this is manifested by processes that can create two photons. And if you measure the polarization of either one of them along any axis, you can rotate the crystal however you want, you get a random result. So it's equally likely to go through the crystal or to be deviated. And then suppose it actually gets deviated here and turns out to be vertical. The other photon will also be vertical. And that means if you were to measure it, it would be vertical if this one was vertical. Now that looks like, and this is what many journalists who don't quite understand this say, is, well, I shouldn't say it's only journalists. Einstein himself referred to this as spooky action at a distance. It's as if this photon becoming vertical caused this one to become vertical also. And that looks like some kind of instantaneous faster-than-light communication. Well, let's try to explain this correlation in various ways. The most obvious explanation is to say that this source is emitting two photons which have the same polarization, but it's not emitting the same direction of polarization each time. It sometimes emits two verticals, sometimes two horizontals, sometimes two diagonal like that, sometimes two diagonal like that. And so they're always emitted in this, and two copies of the same polarization state. Well, that's a good try, but it isn't a successful explanation, because it would say, suppose the source is sometime emitted two of these diagonal photons, but at that instant you've decided to measure them along the vertical and horizontal direction. We know a diagonal photon behaves randomly when it comes to this kind of measuring equipment. So it would be sometimes this one would be vertical and this one would be horizontal. And yet, when you do the experiment, they always come out the same. So this is what's meant by saying that the correlation of two entangled particles is too strong to be explained by imagining that each one has a state of its own. However, it's too weak to be used to send a message. The reason is because this person here cannot control whether this comes out vertical or horizontal. We'll get to that a little bit more later. Well, how would we explain it? Well, the way even scientists speak of it, knowing better, is that they speak as if one of the photons is measured and acquires a state and therefore gives the other one the same state or a correlated state. But that actually is certainly wrong because it implies instantaneous action at a distance. It's faster than light message. And besides, supposing this particle is measured, passed through a vertical filter, it becomes vertical, how does it even know where the other particle is? The other particle might have bounced off a mirror, it might be behind a brick wall. How does it get the message to the other particle? So this is just a wrong explanation. Of course, the right explanation comes from quantum mechanics and says, whenever you speak of two particles, you have to consider the full repertoire of states they could have, which include these entangled states. And these entangled states live in a larger dimensional space than just considering the states of the two particles alone. Well, that again is something that you have a hard time explaining over dinner because it requires considering thinking in 4 dimensions. So a somewhat dangerous way of talking about it is to say, well, actually, when you measure one of the entangled particles, it causes it to behave randomly and send a message backward in time to the moment it was created. So here's the space-time diagram where space goes this way and time goes upward. It says this entangled pair of particles is created. When we measure it, this one decides to be vertical. And then it sends that message backward in time to the moment of its creation, saying, well, the other one should be vertical also. And so when you get around to measuring it, it turns out to be vertical. Well, messages backward in time sound like a really bad idea, worse than faster than light. But they are okay because we're speaking, it's not really a message, it's an uncontrollable message. So it's as if you had a pair of magic coins where they were, however far apart they were, if you tossed them at the same time, you would get the same result. Now you couldn't use these coins would look pretty magic, but you couldn't use them to communicate because the person who tossed this one couldn't make it come up heads. So it's a message backward in time is safe from creating a bad paradox under 2 conditions, and one of them is that the sender can't control the message. That's the entanglement situation. And the other one is this thing that occurs in classical mythology, which is Cassandra had the gift of foreseeing the future. So this is to try to give a feeling for how entanglement behaves. Now, another thing that helps understand it, another metaphor you might say, is that simply classically communicating does not create entanglement. If I talk to you on the telephone, I can't get entangled with you. Some kind of direct physical interaction is necessary to create it. And in a certain way, it's somewhat like human relations also, because it's monogamous. The more entangled 2 particles are with each other, the less entangled either of them can be with anything else. In fact, 2 particles that are perfectly entangled with each other individually appear completely random. Not only are they individually random, but they're also independent of anything else. So it's a randomness that nobody else knows about and can be used as another way of doing quantum cryptography. Well, now what is entanglement good for? Well, one of the things it's good for is quantum teleportation, which we heard about. And that is, suppose somebody comes in with, now time is going this way, somebody comes in with an unknown quantum state and says, oh, deliver it over there to the next building, a single photon. And I say, I'm Alice, I say, well, this is a little inconvenient. You notice it's daytime out there, there's zillions of photons. Why don't you come back with your photon at night so I can send it over to the other building without its getting mixed up with all these other photons? And they say, well, I've got this photon now. Is there anything you can do for me? I want it delivered immediately. And I say, well, fortunately, I planned ahead, and I've shared a pair of entangled photons between this building here and the place you want to send your photon to. So give it to me, and I'll measure it. And they say, oh, no, 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 don't measure it, because if you measure it, you might disturb it. I want to send it in intact form to the other place. I said, well, I'm not going to measure the photon itself. I'm going to measure the relation between it and one member of my entangled pair of photons. And I'm going to do it in such a way that I find out nothing about its polarization. And they say, well, that sounds pretty violent. And I said, well, no, I can prove to you that it won't hurt. And so I measure it, and I get 4 results out of this possible measurement. I've got a measurement of 2 photons, and it gives 4 possible results. And I send those 2 classical bits over to Bob, and depending on what they are, he takes the other member of the entangled pair and rotates it in one of 4 different ways. And if you do the math, it comes out into an exact copy of this state, which has been destroyed here. So we have this sort of disembodying of the delicate information in this state into a classical message that cannot travel faster than the speed of light or backward in time. You can duplicate it as much as you want, but this message tells nothing about the polarization of this photon. But what it does tell is how these 2 photons were related. Well, this one was completely random because it's part of an entangled pair. Essentially, I forced them to choose a relationship which indirectly imposes a relation on these 2, and therefore, if I take this one, I can maneuver it back into an exact copy of the state this one was in before I measured it. So that's how teleportation works. And so you might say teleportation is a little bit like the one-time pad encryption scheme. The private information is a little bit like quantum information. Public information is like classical information. The key is like the entangled pair of particles. And the cryptogram, the ciphertext, is like the classical message in teleportation. So if this were a bit, and it were a secret bit, I could transmit it to this receiving station over this insecure channel by randomly flipping it with this key and then unflipping it at the receiving end. But it's a heuristically useful analogy, but not an exact analogy, because in this case there are 2 bits that have to be sent, not 1. So quantum is you might say is secret. Quantum is an especially strong form of secret. And to preserve this extra strength of it, we need to communicate 2 bits. Well, of course, the real impetus behind this field is not cryptography or the magical things that you can do with entanglement, but the hope of giving Moore's law a new lease on life. And everyone, pretty much for my entire professional lifetime, has been predicting the end of Moore's law. But they probably have some justice in their predictions now, because pretty soon the gates are going to have to be operating with less than 1 electron. And it's hard to see how they can do that. So here is the hope for quantum data processing. And here's an example of a computation which can be done classically, but is extremely hard to do classically. And a quantum computer, because it's allowed to progress through entangled intermediate states, can do the computation much quicker. You might make an analogy to that in something in complex numbers. You know that there's some integrals that are very hard to calculate. They're real integrals. It's a question and an answer about properties of real numbers, like an integral of an exponential, a Gaussian integral. But if you do the calculation in the complex plane, you can find out the answer to this question about real numbers much more conveniently. Well, here's an example of a hard computation. This is a factoring problem. And this number was designed to be hard to factor. I'm not sure who created that number, but they made it by finding two prime numbers that were of course, they could not be factored, and multiplying them together. So you see now multiplication is pretty easy. If I wanted to multiply this number by this number, and I had a quiet weekend with nobody disturbing me, and no computer, I could do it. You know, like 3 times 7 is 21. That's where the 1 comes from. We carry the 2, and so on. In a full day of work and some couple of sharp pencils, and trying it several times to make sure you hadn't made a mistake, a person could do that without a computer. Of course, a computer can multiply those things in a millisecond or less. However, the reverse computation of taking this number and finding what two unique factors it was divisible by took up, I guess it's pretty fast to do now. Well, it's not super fast. But at the time, a few years ago, it took 8 months on hundreds of computers working on it at once. So factoring is very hard compared to multiplication. However, if you do it in a quantum computer, where the input data is classical and the output data is classical, but the intermediate states are quantum, factoring and multiplication are approximately equally easy. So the quantum computer can do this much quicker. And that's why cryptographers are interested in building a quantum computer. So this is an example of how, I suppose this exists in human affairs. You could say that if I want to do a job and somebody watches me too much, it can make my performance less. It shouldn't matter, but if everybody's looking at, you know, supposing I'm doing this calculation, and if they look at all the intermediate results along the way, at least in human terms, it slows it down. But in this mathematical sense, it could be exponentially slowed down merely by not being private, or by being confined to these states which are classical, that is, at each time each bit has a value. If we allow these entangled states, and that is, we're saying we put the data into the computer, we use these quantum gates, we don't let this computer interact with anything else during the course of the computation, the answer comes out quickly, and it does a classical problem that would have been hard to do classically, but it does it quicker. And I'll say maybe in the end why it can do it quicker. Then there's the Grover's algorithm, which is less of a speed up, but applicable to far more problems. It's a quadratic instead of exponential speed up, and it's applicable to any kind of search problem. Well, the ability of quantum computers to do things fast has led to this explosion of proposed hardware for quantum computers. And I think maybe I'll learn something more about this in this conference, because it's one of the subjects is the nano computing devices, which can be at least sometimes used for quantum computing purposes. But this is a hard job, because as I indicated here, while the quantum computer is working, you need to have the qubits inside it interact strongly with each other and yet not interact much with the environment. And that, in fact, at one time looked like a insuperable problem, because there would always be some interaction. And you might say that's the downside of entanglement. It's called decoherence. It says when a quantum system interacts with an environment, it appears to get randomized. And what's really happening is that it's getting entangled with its environment, but the environment is escaping from your control. Now, fortunately, over the last, slightly more than the last 10 years, it's been discovered that this decoherence can be prevented by ideas that are not too different from the ideas of classical error-correcting codes. and they are called, well, quantum error correcting codes. Another related technique is called entanglement distillation. And putting them all together, you get things that are called quantum fault-tolerant circuits. And so this has gotten us to the position where if we make the hardware good enough, then the rest of the error correction can be done in software. So the hardware only has to be finitely perfect. And then beyond that, arbitrarily reliable computations can be done with unreliable hardware. And this is just the same discovery that was made about 50 years ago in connection with classical computing. As you'll recall, those of you who are old enough to remember the 1950s, at that time, computers were made out of vacuum tubes or thermionic valves and relays. And those were unreliable. And sometimes people wanted to do computations that were had more steps in them than the mean time between failure of one of the components. So von Neumann, whom we heard about before, one of his great achievements was showing that you can do arbitrarily long, reliable computations using unreliable parts by appropriate majority voting and error correction in the course of the computation. So the same, now we've forgotten about that because the transistors that computers are made of today are inherently so reliable that you don't need very much error correction to make them work reliably. But in quantum computing, we're back to the way the basic elements that we have to work with are worse than relays, and the threshold of reliability that we need to get these error correcting codes to work properly are higher than they are for relays. So it's a really hard engineering task, but not an insuperable task because it's not making something perfect, it's only making it pretty good. Well, let's see how some of these error correction techniques work. It says if we take an unknown qubit, here's the simplest quantum error correcting code. We take an unknown qubit and we interact it with 4 zero qubits. We get, according to a certain interaction, we get a rather entangled state of the 5 qubits. And you might say, thinking in the 32-dimensional space, we've taken a plane that is a 2-dimensional space of possible states of this qubit and rotated it into a very diagonal direction so that each one of these 5 qubits now looks completely random because it's entangled with the others. Now that looks like it might not be a good idea, but it is a good idea because now if we spoil any one of the 5 qubits and then we undo this rotation, all the damage gets sucked out into these ancillary qubits and you can throw them away, and this one comes out unharmed. So this is a quantum analog of an error correcting code. Now you know if for a classical error correcting code, the simplest error correcting code for a bit is triple redundancy. You repeat it 3 times, and then at the receiving end you take a majority vote, and that'll correct any single bit error. And here we have to have a 5-way redundancy, and I guess the reason for that is that it not only has to correct errors in the zeros and ones, but it has to correct errors in all the superpositions. But aside from this kind of needing more redundancy, the theory of quantum error correcting codes goes through pretty much like the classical theory. Now, entanglement distillation is saying, suppose we have some entanglement and it gets polluted because it's subject to some noise, and so the entanglement isn't perfect anymore. There are protocols involving 2-way communication between Alice and Bob where we take a larger number of partly entangled pairs and come out with a smaller number of very entangled pairs. And putting that all together, there are whole schemes for computation where data, a single qubit, is spread out in this way amongst 5 or more qubits to make it resistant against error. And the computation is done without ever decoding it. And there can be errors in the data here. There can be, this is the thing that sucks this error out and throws it away. And then there can be an error here, and there can even be an error in the computation itself. And all of these errors will eventually be caught and siphoned away. and preserving the integrity of the data even while it's being computed on. Now, what else is quantum information good for? It's good for things aside from computation. Suppose I am a very busy person and you're a very busy person, and we try to find when is the next day when we're both free for lunch. And so the problem of communication complexity is to say how much communication is necessary? What's the volume of data that has to flow between us in order for us to come to a day when we're both free for lunch? Well, it can be shown classically that there's nothing much better than the person with the smaller calendar sending it to the more busy person and then the more busy person picking the date. So if the calendar has n days for possible lunch dates, you have to send about n bits before you can decide which is the best day. But if you have quantum communication, you can do it in about the square root of that amount of computation. So it's as if, and that in fact uses the Grover algorithm, in which the two parties gradually focus in on a date that's good for both of them, even though neither one of them has heard enough information from the other to know when they are free. And then I spoke of teleportation, but another thing you can do with entanglement is to improve the capacity of a classical channel. So if I have a quantum channel, I want to have a quantum channel and I want to send some information through it, and it's noisy, so there's a limit. But now, if I have entanglement, which is not good for communication by itself, I can send more classical information through. Well, so here's an example. It turns out it matters a lot what kind of noise there is. If the noise the problem is that it's a low signal and high noise. Suppose Alice and Bob are trying to hold a quiet conversation in a room full of noisy strangers. Well, then it helps a lot for them to be entangled. They can communicate despite this very noisy conversation going on around them. However, if their problem is that they are alone in a big empty room and a very weak signal going from one to the other, but not a lot of noise, then the entanglement doesn't help very much. So in summary, I would say that quantum information obeys laws that extend the laws of classical information, and that the best way to think even of classical information is this as a subset of quantum information. And indeed, when people speak of the speed up in a quantum computation, probably the better way to think of it is to say factoring is intrinsically an easy computation. It's just that if you try to do it in a classical computer where there's eavesdropping on all the wires, that slows it down. So it's not as if quantum computation speeds up some computations. It's classical computing that slows them down. And maybe it's saying the same thing. But this means that these are very special computations, and that there isn't any hope in quantum computing for a general speed up of all computations. There's some computations that are no faster on a quantum computer than on a classical computer. So quantum computers will not rescue us from the end of Moore's law. And the main reason they're interesting is that there are all sorts of strange phenomena that you can do with them, like teleportation, like enhancing the capacity of a channel by supplying it with something, entanglement, that has no capacity of its own. People are proposing to use entanglement in things like conducting an election so that everybody is confident of who won the election, but nobody knows how anyone voted. That kind of paradoxical seeming problem. Well, how's my time doing? It's done. All right. So I don't want to. This is a good. Yeah. So I can give another. I could say this is another lecture for another time.